In this video, we'll be working with ionic compounds, and we'll be looking at converting between formulas to names, and then from names to formulas. So as a reminder, an ionic compound is a compound that contains either a metal ion or a polyatomic ion, as well as corresponding counterions of the opposite charge. So, to identify these compounds, we need to look at the formula. So let's look at the first case. We can tell that it's an ionic compound because it contains a metal, and metals almost always form positively charged ions, and a nonmetal. This indicates that there's probably going to be a transfer of electrons, as metals tend to lose electrons, nonmetals tend to gain electrons. And so the formula tells us there are going to be two sodium ions produced, and one sulfide ion produced. Notice that this is not a sulfur ion, this is a sulfide ion. The sulfide ion is a sulfur atom that has taken on electron configuration of argon. Now, to form the name of this compound, it's pretty straightforward. What we'll do is we simply combine the cation first, so sodium, and then that of the anion, which is the negatively charged ion, sulfide. Now, we do not use any dis or tris or tetras when we're naming ionic compounds. And we don't need that because of their charges. We know which ratios they need to combine in, because they're always going to combine in a way in which the formula takes on a neutral or zero charge overall. Let's go ahead and work through the next one. In this case, we see that we have another metal, our potassium ion here, but this time we have something that looks a little odd. It's definitely not a sulfide ion because there's oxygen present. And so this entire unit is what's known as a polyatomic ion. And so essentially it's a group of atoms that are bonded together, that together have a net charge, but they act as one unit. And so in a chemical reaction, they will usually stay together and be transferred as a unit. So in this case, we have one SO4 2- ion. And the name for that is going to be sulfate. And again, I've provided you with a list of polyatomic ions to know by heart to help you out with this naming process. So this is one of the ones that you need to know for future use. So as before, we'll go ahead and simply combine the two names of the ions. And this will be potassium sulfate. A similar situation exists for the third one, so I'll go ahead and write that out. We see that there are three potassium ions this time, compared to one phosphate ion. And finally, again, combining them. The next one is a little bit unusual in that it involves the only positively charged polyatomic ion that we're going to commonly use. And so this is known as ammonium. Now, notice that this is different from ammonia. Ammonia is related to it, but it has the formula of NH3 and does not have a charge. The ammonium ion, again from your table of ions to memorize, has a formula of NH4 plus and we can see that it's paired with one chloride ion. To give us the resulting name of ammonium chloride. So this seems pretty straightforward, and it is, especially for compounds in which the cations and anions form consistent charges. And so, for example, calcium is always going to be +2. Sulfur is, for our purposes, always going to have a -2. Where things get a little bit more interesting is when we start to look at substances, or more specifically, transition elements, which can have more than one possible oxidation state or charge. We'll use those terms kind of interchangeably at this level of chemistry. When we take a look at the Fe and O here, we can see that they're present in a 1-to-1 ratio. And so we know that there's going to be one iron ion for every one oxygen ion. And so we have to go to the periodic table. From the periodic table, we could see that oxygen will tend to gain 2 electrons to have the electron configuration of neon. When it does so, it automatically is going to have a 2- charge. And since we know that the overall compound here is neutral, we can deduce that this particular ion must also have a 2+ charge, because the ratio is 1-to-1. Now, if we take a look at the next compound, we can see that it's also made out of iron and oxygen, but they're present in different ratios. So there are 2 irons for 3 oxygens. So this must be 2- as well. And since they're not 1-to-1, there must be a different ratio present. And so it can't be iron with a +2 charge. So the only way for 2 iron ions to balance out a charge of -6 is for them together to have a charge of +6. In order to do so, each of these irons must have a +3 charge. Now, these two types of iron oxide do have different properties, and that comes from them having different ratios of iron and oxygen. And so to distinguish between these 2 iron oxides, we're going to specify the charge on the iron as part of the name. And so in the first compound, this is going to be an iron 2 ion, because it has a 2+ charge. And in the second compound, it's going to be an iron 3 ion, again because it has a positive charge of 3+. The oxide ion is still oxide. And so when we go to write the name, we need to tell the reader which type of iron is present. So the name for the first compound becomes iron 2 oxide. The second compound is iron 3 oxide. Now in the last problem here, I see that I've made a typo, and so I'll go back and fix this for your worksheet. But how we would normally write this compound is as follows, without the parentheses. Again, the parentheses are only present when we need to have multiple ions of that particular type present. And since there's only one SO4 here, it's not necessary to put it in parentheses. So this one we start naming just as always. It's going to be an ionic compound composed of magnesium and SO4, which we remember from before has a -2 charge. So this is going to be a sulfate ion. Magnesium, due to its position on the periodic table, is a +2 charge and is simply the magnesium ion. Notice that we don't have to put a Roman numeral after the magnesium because magnesium is always going to be +2. So we'll name the first half of the compound, and that's going to be magnesium sulfate. But now we have to pay attention to what's happening here, because in this compound it's not just magnesium and sulfate ions. There are waters, 5 waters, that have been combined there. And so this particular type of compound is known as a hydrate. So when this compound forms, water is actually incorporated into its crystalline structure. And so we show that in the name as follows. We see that there are 5, and the prefix for 5 is penta, and so this becomes magnesium sulfate pentahydrate. Now, I'd like you to try these next compounds on your own, and then compare your answers with those answers that I've provided in the key at the end of your worksheet. Please pause the video. In this next part, we'll be writing the formulas of compounds based on a given name. For the first compound, we see that it is composed of lithium, which has a +1 charge based on its location in the periodic table, and oxide. So again, oxygen is going to have a -2 charge based on its location. As discussed earlier, we saw that the overall formula for a compound needs to be electrically neutral. So this tells us that we need to have 2 lithium ions present for every 1 oxide ion to balance its charge. To write this in a formula, we're going to indicate with a subscript that there are 2 lithiums for every 1 oxygen. And whenever a subscript or a coefficient is equal to 1, we leave it off. It's assumed to be present. In the next compound, we're working with aluminum. So again, based on its location on the periodic table, aluminum forms a +3 ion. Sulfate is one of our polyatomic ions to memorize. And we notice that they're not going to react in a 1-to-1 ratio. So we have to see what number do they both have in common. So their least common multiple is going to be 6. So in order to balance charges, we're going to need 2 aluminum ions for every 3 sulfate ions. Now written as a formula, we'll indicate it as aluminum, subscript 2, sulfate, parentheses 3. Notice that this time we need to include the parentheses. For the third compound, we're going to use ammonium, again, the only positively charged polyatomic ion we'll commonly work with, and phosphate. So PO4 3-. We can see that there'll need to be a ratio of 3 ammonium ions for every 1 phosphate ion. In number 4, magnesium nitrite, magnesium has a +2 charge due to the periodic table location. Nitrite is one of the polyatomics that we need to memorize. The ratio will need to be 1 magnesium for every 2 nitrite ions. Moving down, we have a transition metal, so we have copper 2 phosphite. Since it's copper 2, we know that we need to include a charge of 2 plus on the copper. The phosphite is one of our polyatomic ions, and it's similar to phosphate but not identical. We can see that again, a 1-to-1 or a simple 2-to-1 ratio is not going to work for balancing charges. And again, the least common multiple is going to be 6. So we're going to need 6 positive charges carried by 3 copper 2 ions to balance 2 phosphite ions. In the next compound, we're working with chromium 6, so that's going to be Cr 6 plus and oxide 2 minus. In order to balance charges, we could see that for every 1 chromium 6 plus, we are going to need 3 oxide ions to balance. And in the final example, we're working with iron 2 chloride. So iron 2 chloride with a -1 charge based on the periodic table. Fairly straightforward ratio here. So 1 iron 2 ion to 2 chloride ions. And now for the formula. FeCl2 with, and then we look at the prefix of tetra, which means 4. So we add 4 H2O to finish off the formula. Now I'd like you to pause the video and try these compounds. When you are finished, please compare them against the key that I've attached to the back of your worksheet.